Dr. Indradeep Kumar, Assistant Professor, IARE, Hyderabad. So in previous video, we had seen the last module of the second module, right? So in this video, we will see the third module, which is unsymmetrical bending. So first, we'll cover the topic about what is unsymmetrical bending. So first, let's come with the unsymmetrical bending. We have shown that the value of direct stress at a point in the cross section of a beam subjected to bending depends on the position of the stress here. What we had seen earlier, value of direct stress at a point in the cross section of a beam subjected to bending depends on what? Position of the point, means where the load is applied, the applied load and the geometric properties of the cross section. So it depends on what? Where the load is applying and the geometric property, that thickness area A B into T. Just we use in the thin plate, right? So it depends on where the load is applying and geometric property of the cross section. It follows that it is of no consequences whether or not the cross section is open or closed. So here does not matter either the cross section is open or closed. What is the area of the cross section is there that matters here. It's not about it's a closed or open. We therefore derive the theory for a beam of arbitrary cross section and discuss its application to thin-walled open and closed section beam subjected to bending moment. So what we will do, that for thin wall, open and closed section, we can just derive. The only difference is what? In the closed section, wherever the closed beam is there or closed section will be there, their internal stress will be there or internal pressure will be there. So generally we are talking about the solid, so internal stress will be there. That is called the hooked stress. So when the solid beam will be there or closed section will be there, that time we can say we have to just add the hooked stress. So what we will do, we will derive for the open section or open beam, and in that we will just add the hooked stress terms that will be for the closed beam section. So just see. However, before we derive an expression for the direct stress distribution in a beam subjected to bending, we establish sign convention for moment. So moment will be positive, negative. So first sign convention of the moment, force and displacement. Investigate the effect of choice of section on the positive direction. So in what section is simply just the how the bending moment will be positive and negative, or you can say sign convention of the bending moment, force, displacement, these things. Discuss the determination of component of a bending moment applied in any longitudinal plane. So what will be the direction? Positive will be the positive bending moment, when will be the negative bending moment, force, displacement and all. So consider, so now this is direct stress distribution due to bending. So consider a beam of having arbitrary cross section, means any cross section is like this shape. No, there is particular, either it's a spherical cross section or that rectangular square or anything. Any arbitrary section that gives what? The thickness of this, and whatever the length is there is according to that only whatever the cross section is there. If suppose it's a circular, then their cross section will be pi r square. If it's rectangular, then length into width or width into thickness. If it's a square, that's square. So that depends on the type, but generally what we are deriving for the arbitrary cross section. That arbitrary can be anything depending upon the given condition. The beam supports bending moment mx and my and bent about some axis in its cross section, which is therefore as axis of zero stress or neutral axis. So here along this, and earlier also we had seen along the neutral axis zero stress is there. So that's why neutral plane remains neutral even after applying the bending moment or before applying the bending moment or before applying the forces. Whatever is there, that remains same. So in one plane will be there or one axis will be there, that is only called the neutral axis. Let us suppose that the origin of axis, so this is the plural of that one, axis coincides with the centroid C. So now wherever the centroid of that member is there, right, what we are considering, the either beam or anything, where is the centroid of that one? So there we are supposing that origin also at the centroid only is there, okay, cross section, and that the neutral axis is a distance P from C, and that cross section and that the neutral axis is a distance P from C. So from centroid at a distance P, that is there. So direct stress sigma z on an element of area del A at a point x comma y and a distance x from the neutral axis is. So simply from the Hooke's law, sigma z equals to E into epsilon z. Sigma z along with z. So E into epsilon z. Epsilon z is a strain. From Hooke's law, stress is directly proportional to a strain, or the strain is equals to Young's modulus of elasticity into the strain. If the beam is bent to a radius of curvature r about the neutral axis at this particular section, since plane section are assumed to remain plane after bending. First assumption itself is there. Plane after bending also it remains plane, that neutral plane after bending, and by a comparison with symmetrical bending theory, that epsilon z equals to zeta by rho. So from this one, that strain will be what? Zeta by rho. Now just substitute this value here. So what you will get? Sigma z equals to E into zeta by rho. Okay. So here sigma z equals to E into zeta by rho. So now just see here. What is given there? See where the centroid is there. There only we assume that is what? At a distance. This coincides with the origin of centroid of this one. And here we have taken that one. Now this is the neutral plane, right? Okay. So which is not getting bent or not experiencing any stress. So from here neutral plane, what we have that measure, suppose at some distance zeta, that we have taken a small elemental dA which is at a distance y from this one. And what is the neutral plane axis from the origin? That is this P, or you can say this rho. Rho is the distance from CG to this neutral axis. Okay, so this is in this case it's a zeta, and from this side at a distance x, just coordinate. So this will be the x comma y. Okay, now shift this neutral plane to at the origin. Earlier neutral plane is here, right? Now just shift this C here, or this neutral plane to here in this case. So now this is the neutral plane. So from neutral plane only we are taking this distance zeta. So from neutral plane to this will be zeta. So that is the here case, second case. So from the neutral plane, now this neutral plane is passing to the origin. This is neutral plane and origin is different. But in this case now neutral plane is passing through the origin. So from neutral plane to this distance is zeta, and again from here the axis is at a distance y, at a distance x, and that neutral plane is that at an angle alpha. So here that alpha was not there because along this only we have taken. Now this origin is at angle alpha from the neutral plane. So that we have to take care. So in this case, that axis is at an angle alpha from the neutral plane. Okay. The beam supports pure bending moment, so that the resultant normal load on any section must be 0. So whatever is there, if it at equilibrium, it must be equals to 0. So that's why over integral over entire area sigma z dz equals to 0. So the sigma z into dA is what? Force. So force should be equals to 0. Therefore replacing sigma z in this equation, right? So sigma z will be equals to what? Sigma z will be here, zeta into d, or just sigma equals to epsilon. So just here from this one, sigma z equals to E into zeta by rho. So put here. So sigma z E into zeta by rho into dA equals to 0. E by rho is constant, out of integral E by rho, that is zeta into dA equals to 0. So take this as E integral zeta into dA equals to 0, cross multiply. So integral over A zeta into dA equals to 0 by E. That also is 0. So the integral zeta into dA equals to 0. This is the first moment of area of the cross section of the beam about the neutral axis is 0. So this is first moment. Now moment of moment, that area moment is called only the moment of inertia. So right now this is the first moment. Okay. So first moment of area of cross section of the beam about the neutral axis is 0. So that first moment will be 0. It follows that the neutral axis passes through the centroid of the cross section, which is the result we obtain for the case of symmetrical bending. That symmetrical bending already we got this equation. Suppose that the inclination of the neutral axis to Cx is alpha. So here, measured clockwise from Cx, the centroid of that angle is alpha. That I showed you here, that angle is alpha. C to x. Okay, that is, this is Cx. Right, Cx. So Cx at an angle alpha from the neutral plane. Then from that same, zeta equals to x sine alpha plus y cos alpha. The direct stress sigma will be equals to what? E by, what was the condition? Sigma z equals to E into zeta by rho. Right? So zeta, put the value here. So this is E by rho into x sine alpha plus y cos alpha. So that is your sigma z. Okay. The moment resultant of the internal direct stress distribution have the same sense as the applied moment mx and my. Therefore, so whatever moment is there in that same sense. So mx will be equals to sigma z y dA and my will be sigma z x dA, because along the x-axis then y dA will be the area, along the y, so x dA will be the area. And this, so mx equals to sigma z y dA, my equals to sigma z into x dA. Now just substitute the value of sigma z and integrate it. So see here, what we got. First we are solving for mx. So mx is equals to what? Mx equals to close integral over area sigma z y dA. What is sigma z? Here, E by rho into x sine alpha, okay, plus y cos alpha, okay, into y dA. Now sine alpha is constant, cos alpha is constant. So after multiplying, just first multiply this one. So E by rho sine alpha into x, and I am multiplying this also, y dA, plus E by rho y cos alpha into y dA. Now integral over entire A. So now we are separating this integral. So E by rho sine alpha is constant, so out of integral. So E over area A. So here E by rho sine alpha from this term. What is xy into dA? So xy dA, right? Plus, now this is E by rho, okay, into cos alpha constant. So then this will be y square dA. Okay, so now integral of this is what? X, y dA was the first moment, right? And into x, so moment of moment. So this xy will give what? Ixy. And here y square is Ixx. So now after putting this value, what you will get? E by rho sine alpha into, this is for Ixy, plus E by rho Ixx, sorry, here cos alpha, right? So just here, E sine alpha by rho Ixx plus E cos alpha by rho Ixx. So here xy, here x. So xy, x. So this is for what? Mx. Now similarly we can find for what? My also. So now the my equation is this one. So let's put first my equation. So my is what? My is integral of A sigma z into x dA. Now put again the sigma z value. Sigma z is what? This one. So equals to here E by rho x sine alpha plus y cos alpha, this is into x dA, right? First multiply all this simultaneously. So I am multiplying this to this one and at the same time this also to all the term. So E by rho x sine alpha into x dA plus, now with this E by rho to this term. So E by rho cos alpha into E by rho y cos alpha into x dA. So from here what we will get E by rho sin alpha into x square dA plus E by rho cos alpha into yx dA, the whole integral from A. Again separating, so let me write here A also. Okay, so after this E by rho sin alpha is outside because constant. E by rho sin alpha constant, what we have, A equals to x square dA plus again same here E by rho cos alpha out of the integral A y x dA. So integral of A x square dA is x square, means it's I y. So from here what we will get, this is our I y and this is I xy. So from this what we will get, that is E by rho sin alpha into I y plus E by rho cos alpha into I xy. So see now, E sin alpha by rho into I y plus E cos alpha by rho I xy. So now why we have mx and my in terms of what? Moment of moment, that is moment of inertia. So E is what? Young's modulus of elasticity, that is constant. Sin alpha at angle alpha degree. That's why in that earlier we had seen that it's adjusting by themselves from 45 degree to 40 degree, 38 degree. In case of other, because it's 45 degree, no wrinkle will be there. Both sides it should be same. So it's just adjusted less than that one. So if for normal it's a 40, but for aircraft structure, it around 38 degree it is. Right. So means according to the moment of inertia, the bending moment will be there along the x-axis and along the y-axis. Right. Now same thing written in matrix form. So mx, my is that we have to find. E by rho is constant. Ixy, ixx. In first equation just here Ixy and Ixx is this. Mx, E by rho is constant. Ixy, Ixx for second, Iyy, Ixx, and then sin alpha, cos alpha. So the same two equation, this one can be written in the matrix form as this one. Now what we have, just take this, keep this side, this to this side, and take this side, this Ixx to this side. So now what happened? This will be inverse of that one. So E by rho sin alpha cos alpha is equals to inverse of this one into mx my. Now inverse of this one you have to find this word, adjoint of A by determinant of A. So adjoint of A is cofactor of A. First find cofactor, they take the transpose of that one. So after finding the inverse of this one, what you will get? Just here, adjoint of A by determinant of A into mx my. So this is E by rho into sin alpha cos alpha equals to 1 by, that's just the determinant of this one, Ixx Iyy minus Iyy Ixx, right? So yeah, so Ixx Iyy and Ixy, so this becomes Ixy square. Okay, so this is the determinant of this one. So after this what we can write, finally the direct stress sigma z is given by sigma z. From here what we can say, so here sigma z we found here in terms of m, right, or sigma z from here, right, that is sigma z into this one, or from here E by rho x sin alpha cos alpha. So from there what we will get, sigma z equals to my Ixx minus mx Iyy by this one, just cross multiply. So mx Iyy, that is minus, so here, and mx Ixx here, right? For this term mx Iyy minus my Ixx by this. So just this is the multiplication of this one, that sigma E by rho sin alpha was there. So that's sigma z equals to this one. Okay, just see quickly once again. So now direct stress distribution due to bending we have to find. So according to the Hooke's law, sigma z equals to E into epsilon naught. right? So epsilon, here sigma z we have taken, that sigma z equals to E into epsilon z. But now what happened, that we assumed according to the compression that epsilon z equals to zeta by rho distance is there. So that's in, let's substitute zeta by rho in the stress equation. So sigma z equals to E zeta by rho. Here in figure what we have seen, the first case was, here the CG is there of this arbitrary section, and one plane is there, that neutral axis plane, along which the bending moment is zero. I'm not experiencing any moment before bending and after bending. So in case from this point we have taken at a distance zeta, right, that small elemental strip, which is from this side it is at the x, and from x-axis at a distance y. So this is the first case, and from the neutral, that is from the centroid to this neutral axis distance was rho. Now if this coincides, means this rho becomes equals to 0. So what happens, neutral axis and centroid will coincide, right? So now from here to this distance, that is from the neutral axis, because from neutral axis only we are taking this distance. So neutral axis to this distance will be zeta. From the y-axis it's x, from x-axis it's a y. That other things are okay. Now one more thing is here, that this axis, that origin of this axis are at an angle alpha from the neutral axis. But here we are not taking that as reference. This was reference. So but here in this case, that coordinate axis is at an angle alpha to the neutral axis, or you can say Cx is at an angle alpha from the neutral axis. So from that only what happened, whatever the forces is acting, that must be equals to 0, then only it will be what? In equilibrium. So that force, that is sigma z into E, is equals to 0. Now just substitute here, that is given, that sigma z value as E into zeta by rho dA. So E by rho is constant, so out of integral. So out of integral means zeta dA will left, E, this rho this side multiplied 0, E. So finally zeta into dA equals to 0. From here also, that is mentioned here, Cx is alpha from the this one. Now according to from the figure again, zeta equals to x sine alpha plus y cos alpha. Let's substitute in sigma z value. So sigma z is here in this value. Let's substitute that zeta value. So after substitute, what we will get? Sigma z equals to E by rho into x sine alpha plus y cos alpha. Now we know that moment will be what? Mx and my. So mx will be equals to integral over entire area A sigma z y dA, and my is equals to integral of over A sigma z x dA. Now put here sigma z value in both the equation one by one. So after putting sigma z, take common out, then that will be this. In this case, first Ixx will be there and Iyy will be there. According to that, after simplifying, you will get mx equals to E sin alpha by rho into Ixy plus E cos alpha by rho into Ixx, and my will be equals to E sin alpha by rho into Iyy plus E cos alpha by rho into Ixy. So now we have mx and y. Now from this we can find the sigma z also. So same equation we can write in integral determinant form like this. Now take this side, because E by rho sin alpha by cos alpha, because that is only here. After substituting this, right? So or just sigma z in this case. So what we will do, we will take this to this side. So this becomes mx my and inverse of this one. So E by rho sin alpha cos alpha, inverse of this one. What is inverse? Adjoint of that matrix divided by determinant of the matrix. So adjoint of this is here, this matrix, and this is the determinant of the matrix into mx. Now just multiply. So after multiplying this, like this we are multiplying. So minus Ixx minus Ixy into mx plus Ixx into my. Similarly for this one, Iyy into mx minus Ixy into my. So after multiplying is here. So that is sigma z equals to my Ixx minus mx Ixy by, because this will be common for both. So Ixx Iyy minus I square xy into x plus mx Iyy minus my Ixy by Ixx Iyy minus I square xy into y. Okay, clear? So this is for the direct stress, that sigma z. So what we did first, we found that mx, my, and then substituted to find the direct stress sigma z. So here is your reference. If you have any doubt, you can just comment on the video, or you can just contact me so that I can clarify your doubt. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.